Welcome and good morning to my talk at Unite Amsterdam. It's great to see so many faces here. I actually expected like 5 people because it's so early in the morning and it's the day after the party. So it's great to see a lot of people of you interested in how to render faster for virtual reality. So my name is Dominic Eskofier. I'm the head of virtual reality for the EMEA region at Nvidia. And today I'm going to talk a little bit about the rendering challenges that you guys face when building your own virtual reality apps. And bear with me, some of you might have seen a little bit of this content before, but it makes sense to reiterate this because Nvidia has put a lot of work into making virtual reality render faster on their GPUs, and I want to reiterate a little bit on that, but there's going to be new content as well, so don't fret. All right, most of you probably know this, VR requires a lot of things that are different from traditional gaming, and one of them is ultra-low latency. So if you're taking the headset movement and then you send that to the CPU sends the processed data to the GPU, which then sends the rendered image to the headset. You will want to have a motion to photon latency lower than 20 milliseconds. So a couple of studies have shown that as long as that perceived latency stays within under 20 milliseconds, you actually get a good experience and you're mostly free from motion sickness or nausea that you get from a higher latency in virtual reality. Another thing that comes into play in this is that in the future, and already now available, there's wireless kits for those headsets. So for example, the TP-Cast or the Display Link for the HTC Vive allow you to run the headset completely wirelessly. And that also adds a bit of latency. So you really have to squeeze as much out of the pipeline as possible to make the perceived latency as low as possible. Another thing that's very important for virtual reality is performance. So if you take a look at traditional gaming on a PC monitor on a full HD monitor, you're looking at about a bandwidth of 60 megapixels per second. So that's the amount that you have to push through the pipeline. If you're looking at virtual reality, you render for 2 eyes. You have a render target of 324 by 1680, and you're also running that at 90 frames per second. So the demand for virtual reality applications in terms of performance is way higher than traditional PC gaming. It's 7 times more demanding. So how do you actually manage to run on existing hardware and still get that performance boost that you need? And the solution for that is VRWorks. It's a concise suite of tools that we are pushing out to developers to actually help them with their virtual reality app development. And VRWorks, I'm going to go into the details of this. VRWorks is a set of tools that's also available for Unity now. So it was available as a plugin before, but now it's getting mainlined with Unity 2017.1. And it includes features like multi-res shading, lens match shading, single pass stereo, and VR SLI. And I'm going to go into detail on all of this in a bit. And again, bear with me, most of you know this, but for those who don't, graphics are rendered, so the traditional graphics pipeline looks a little bit like this. You create 3D geometry, then you project that 3D geometry onto a 2D view, which traditionally is your gaming monitor, and then you calculate the pixels from the pixel color values and so on and so forth. In VR rendering, you're doing a special thing is you're looking at the screen through a set of lenses, and by doing that, you're essentially rendering black pixels, which does not really make sense. So if you take a look at the image here, you see the outer parts of the image. They'll never make it to the user's view because the lens unwraps those pixels, and then they land in the periphery where you don't even see them. And if you take a look at the green circle, you can see that the center part of the image is relatively undistorted, but the outer parts are way more distorted. And what that means is you can essentially save fidelity when rendering, because in the end it gets squeezed in anyway, and this way you actually lose image information. So what you can do is you just split the rendered image up into 9 different viewports. It's a very basic way of saving on those outer parts of the image. And what you do is you render the center viewport at full resolution, and then you render the outer parts at a lower resolution. And essentially, because again, the virtual reality headset unwraps that image, you don't see a difference in VR. The only thing you can see is a little bit, if you're looking very closely, is the line between the central viewport and the outer viewport. So if you take a very close look, you'll see that. And this was actually introduced in Maxwell, and we've came up with something called lens match shading that it was introduced in our Pascal generation of graphics cards. And this again gets rid of the problem that you see the difference between the low resolution and the high resolution part. And we're doing that by rendering to a viewport that is correct on that is closer to the lens corrected surface that you see in the headset. And what you get here is there is no line between like a low resolution and a high resolution part. The pixel density actually has a linear curve along the paths from the left to the right, as from the center to the outer parts, and from the center to the top and bottom parts. Another thing that you can do is you can do single pass, a thing called single pass stereo. So if you look at traditional stereo rendering, you require 2 geometry passes, one for the left eye and one for the right eye. What you can also do is, and that's single pass stereo, you can actually just do 1 geometry pass and then extract the different eye information from that 1 geometry pass. So in essence, what that means is you can either have twice as much geometry in a scene, or you can use that freed up performance for other tasks like effects or different other things. So this gives you a little bit of an overview of what we're doing. We're putting less load on the pixel shader with lens matched shading, and we're also putting less load on the geometry part of the pipeline because we're using single pass stereo. And these two things in most of the apps, these two things alone in most of the apps free up 20 to 30% of performance. So instead of going in and doing a lot of optimization steps, you can get up to 30% performance right out of the bat by just essentially getting VRWorks running in Unity. And then there's also VR SLI. So most of you probably know SLI is a method of using 2 GPUs and then run them to render alternate frames. And this is what it traditionally looks like. The GPUs render alternate frames. So GPU 1 renders all the odd frames, and GPU 2 renders all the even frames. And this is actually good for traditional gaming. It's completely fine, but it adds more latency because, as you can see here, and in the next slide, you can do a different thing where you're using the GPU 1 to render the left eye and the GPU 2 to render the right eye. Sorry, GPU 0 and GPU 1. And this actually saves on latency as well. And as I said before, latency is one of those things that you really want to keep low in your virtual reality experience. And I've pulled out an example from Viking Village, and this is only using multi-res shading. So only the tech that we already had in the Maxwell generation of GPUs. And as you can see here, there's a 30% performance boost in Viking Village just by using multi-res shading alone. So it's really a tool that's helpful, that brings you a lot of that saves you a lot of optimization steps in the long run. Here's a little overview of Unity of virtual reality apps that are built with Unity. So the message that I'm trying to transport here is, if anybody of you, and actually I would like to ask that question, how many of you are VR developers? And how many are just general developers? Okay, how many of those general developers are looking into virtual reality for any of their future projects? Right, that's good. So next year when I'll be here, that's probably going to rise all the hands when I ask the first question. That's nice. So the message I want to transport is, if you're not doing virtual reality yet, but Unity is your engine of choice, then it's really, really easy because Unity has a lot of features that make development for virtual reality super easy. And you can see that by the broad range of virtual reality apps that are out there at the moment that are using Unity as a tool to put to get together their virtual reality apps. One of those that I want to point out is Space Pirate Trainer. I'm not sure if any of the developers are here. That's a great game that's working with Unity. They're using a ton of features they're building in their own Boyd engine, which I heard only yesterday. There's things like Job Simulator or Fantastic Contraption that were launch titles for the HTC Vive and the Oculus Rift. And as you see, there's a ton of content already being produced in virtual reality with Unity, and most of you will probably agree, those who've worked with Unity in VR, it's relatively easy to get your app working with headsets. So a little bit about the Unity integration. It's a native plugin, so it's like I said, it's going to be mainlined in 2017.1, and it's actually really easy to put it in. So the Unity scripting language is used to access the features, and I just want to give a little bit of an example on the next slide of how you integrate VRWorks with Unity, or how that changes the scripting you put in. So we have an SSAO example here, and this is how it looked before. And if you want to call the functions from VRWorks, it actually looks like this now. So you use the VRWorks remap UV and the VRWorks clamp UV, and then essentially everything else gets done by the SDK. One more thing that I want to show you is FCAT VR, which I think is actually really important for virtual reality development. So in VR, you want to make sure, of course, that you're not dropping frames, because that gives you a very unpleasant experience in virtual reality. And you also what you don't want to do is do reprojection or synthesized frames. So as soon as your virtual reality app drops below the native frame rate of the headsets, which is 90 FPS for the Oculus Rift and the HTC Vive, you're dropping down to 45 FPS, and all the other frames get synthesized. And it works, but it's not the most pleasant experience. So if you really want to have a solid experience where objects in virtual reality feel solid, they don't blur, you do want to avoid those synthesized frames at all costs. And another part that's kind of complicated is actually measuring the HMD. So how do you measure from start to finish whether you got dropped frames or synthesized frames on a hardware level? And if you wanted to do that before, actually you had to have a whole setup for capturing that information. So essentially, you're using the GPU's HDMI out. You split that both to the HMD and to a capture card, and then you also need to monitor the HMD system, because otherwise it's a little bit complicated. So this is what it looked before, and FCAT VR actually allows you to do all of that with software. And the way this works is usually you take a video of the app that you wanna analyze, and then you run it through you run it through a VirtualDub or another video tool to see frame by frame whether you're actually whether you're actually dropping frames or synthesizing frames. And if you're taking a look at what we're doing now, is we're taking all the stuff that you had to have before and put that in software. So essentially, it looked like the left side before, and with FCAT VR you can analyze your frames in a much easier way. And we made sure that our software is giving out the exact same data than a hardware capture system. And when we announced FCAT VR, we had a couple of tech review sites test the FCAT tool to make sure that we're not cheating in any way, we're not changing the numbers in any way. FCAT gives you exactly the same result that a complicated hardware tool would give you. And then if you run that through FCAT, you can actually do a lot of data analyzing with FCAT data analyzers. So this helps you to take a look at the frame times. This gives you exact information about everything you need, and this way you can really get down to the nitty-gritty details of where the drop frames are coming from and how to avoid those in virtual reality. Because as I said, it's a tricky thing if you have drop frames in VR. It gives you a negative experience. So this was a little bit of an overview of the graphics side of things. And if you guys are interested, VRWorks is actually a much bigger suite of tools. So essentially, I talked about the graphics side of things, where lens match shading helps your pixel shader. Single pass stereo puts less pressure on the geometry side of the pipeline. You have multi-res shading to save on pixels, and also VR SLI to drive your app at maximum performance. But then there's a couple of other things that are also included in VRWorks. So things like context priority, direct mode, front buffer rendering, those are all professional. They help professional application developers to put in to get the most performance out of their VR applications. There's things like VRWorks audio, because audio in VR, and probably many of you will agree, is very important. So for that immersion, you really want a sound source to sound exactly where you expect it to be. So for example, if in your app a tank is rolling from the side, or a bullet is swishing by your head, you really want to hear that and want that to come from the exactly right direction, because the human brain is very much trained to knowing exactly where a sound is coming from, and also by things like reverb, your brain also knows in what kind of environment you're in. So if you're in a church, sound is completely different than, for example, this exhibition hall or like a small room. And your brain is actually very well tuned to that. And so we always want to make sure that the immersion is on point, that it's as good as it can be, and audio is a big part of that. And so we also put together a suite of tools that's called VRWorks Audio, and it takes our existing ray tracing engine called Optics and uses that to path trace audio. So essentially, it's a very sophisticated way of doing 3D audio in virtual reality. We also have a set of tools for physics, and also professional things like warp and blend, synchronization, or GPU Direct for video. If any of you guys are producing video, 360 video or anything like that, that is also helpful. If you have any questions about those things that are not on the graphics side, you can approach me later on, or check out our website, which I'm going to put in URLs for later on. Just as a quick example of what physics can do for you in your virtual reality app, we recently announced advanced physics simulation through our flow system, and Flex and Flow system. So Flex and Flow is a tool to enable particle effects in engine, and those all those things are also already included in the Unity in the Unity version of in the VRWorks version of Unity. So if you have more questions about advanced physics simulation, we also have a booth out there where we're talking about how you can make use of those physics tools in your app. There's also my good colleague George Scotto sitting over here. If in case you have any questions, he's also very well literate on that whole topic. And I just want to put a little bit of a spotlight on this, because again, if things feel wrong in virtual reality, so if fire, for example, isn't behaving the way you would expect it from real life, the immersion is there's a break in immersion immediately. So essentially, if you're, for example, doing other physics simulation like fluid simulation or destructible objects, and they don't behave like you expect. So, for example, if you splash a bucket of water on the floor, or you shoot with a paint gun, and the paint or the fluid isn't behaving exactly like you'd expect it to be, immediately you lose that sense of immersion because you feel that something's wrong. And so physics is just like audio is one of those things that is very important. So it's not only about the visual side. So if you want more info on Unity and VR, this is probably the slide that you want to take a photo of. The VRWorks plugin for Unity is available on the Asset Store right now, and as I said, it's going to be mainlined in 2017.1 soon. We have a whole developer website on the VRWorks SDK itself, so you can check that out. And for the physics simulation, you want to take a look at the GameWorks SDK, which is also available on our developer network. And we just revamped those websites. So the VRWorks developer website now has all the, well, I hope all the information that you guys need for building your apps, and it's a very good source. So there's tutorials, there's documentation, everything that you need to get the most out of your virtual reality application is inside the developer network at Nvidia. All right, that's it from my side for the presentation, and I'm now open for questions from the audience. Sorry? So the question is, what about AMD? Huh. So the VRWorks SDK that we're putting out is essentially made for Nvidia GPUs. So it uses special implementations on our hardware. So it's not an easy task to have it run on AMD GPUs. And I know you're a developer crowd, and you probably love open source, and I do the same thing. So I'm very much of an open source guy. And usually I have kind of a hard time when it comes to selling proprietary things like this. But in this case, Nvidia has a really high market share in virtual reality. So over 90% of your customer base are using Nvidia GPUs when going for virtual reality applications. And so, as much as I love open source, I also am a huge virtual reality enthusiast. And as long as those things make the experience better for over 90% of the virtual reality crowd out there, I can actually stand here with not much of a guilty conscience. I can say this is making the life of 90% of virtual reality users better. So I can actually be here and say this is a good thing for you to put into your applications.
I've been trying out VRWorks.
Cool.
And currently, if you use Steam VR for Unity, with the latest version of Unity, then the controllers don't get rendered.
Okay.
And the workaround for that breaks VRWorks. So the right eye doesn't render anymore, it turns black.
Okay.
So currently I'm unable to use VRWorks to port my existing application.
Okay, and that's something that's reproducible?
Yeah, absolutely.
Okay, can you approach me afterwards, or I'll just grab you, because that's one thing I definitely want to get forward to the tech team, because that shouldn't happen.
Okay.
Thanks.
I'm kind of curious about the overhead of FCAT. Is there any overhead for?
Actually, I don't know the performance numbers, but as far as I know, it's a very lightweight tool. So it's actually made not to impact your virtual reality performance, because then it wouldn't really make sense if you're using an additional tool that pulls off a lot of performance. That wouldn't make sense. So we're trying to. I don't have any numbers, so don't quote me on that. But I'd say that it's a very low impact on the performance of the app itself.
All right.
We just want to know, can I use VRWorks with the native Unity VR implementation, Steam VR and Oculus SDK?
Yes, you can. We're actually working together closely with Oculus, and Unity. It's going to be mainline in Unity, so it's native starting from 2017.1.
Okay.
Cool. Then thank you for your attention, and have a great Unite Amsterdam.